Hey everyone, tonight we're diving into something that's going to completely shatter everything you think you know about the universe. What is space actually made of? And before you say empty nothingness, let me stop you right there. Because that answer is so far from the truth, it's almost laughable. Space isn't empty. It's not a void. It's actually one of the most complex, dynamic, and mind-bending environments in existence, packed with invisible forces, mysterious particles, and energy fields that would make science fiction writers jealous. So grab your favorite drink, get comfortable, and let me know in the comments where you're watching from tonight. It's always incredible to see our community spanning the globe, all united by curiosity about the cosmos. Tonight's journey is going to take us from quantum fluctuations smaller than atoms to dark energy stretching across billions of light years. And trust me, by the end of this series, you'll never look at empty space the same way again. Now, here's what's absolutely wild about this topic. We've been staring up at the night sky for thousands of years, thinking space was just the stage where stars and planets performed their cosmic dance. But modern science has revealed something far stranger. Space itself is the main character in this story. It's not passive emptiness waiting to be filled. It's an active participant in every single event that unfolds in our universe. From the birth of galaxies to the quantum interactions happening in your own body right now. What I'm about to share with you comes from decades of cutting-edge research, from the most powerful telescopes ever built to experiments conducted in underground laboratories. Scientists have discovered that space contains at least 5 major components, each more bizarre than the last. And here's the kicker, the stuff we can actually see, all the stars, planets, gas clouds, and galaxies, represents less than 5% of what's actually out there. The remaining 95% consists of substances so strange that we're still trying to figure out what they even are. But let's start with what we thought we knew. For centuries, scientists believed in something called the ether, a mysterious substance that filled all of space. They needed it to explain how light could travel through the vacuum. After all, sound needs air to move through, so light must need something too, right? Wrong. The famous Michelson-Morley experiment in the late 1800s proved there was no ether. Light didn't need a medium. Space really was empty, or so we thought. Fast forward to the 21st century, and we've discovered that space is anything but empty. It's absolutely teeming with activity. Every cubic centimeter contains energy fields, virtual particles, radiation, and forces we're only beginning to understand. In fact, calling space empty is like looking at a bustling city from 30,000 feet and concluding it's deserted because you can't see the people. Let's talk about the first major component that fills space, and it's going to blow your mind. Dark matter. This invisible substance makes up roughly 27% of everything that exists in the universe. 27%. That means more than a quarter of reality consists of something we cannot see, cannot touch, and have never directly detected. We only know it exists because of its gravitational effects on everything we can observe. Picture this scenario. You're watching a dance performance, but you can only see one dancer. This visible dancer is spinning, leaping, and moving in ways that suggest they're dancing with a partner. Sometimes they're lifted into the air by invisible hands. Sometimes they're spinning around an invisible axis. The choreography only makes sense if there's another dancer there, one you simply cannot see. That's exactly what's happening with galaxies and dark matter. Galaxies are spinning so fast they should tear themselves apart. The gravity from all the visible stars, gas, and dust isn't nearly enough to hold them together. Yet there they are, stable and intact, spinning at impossible speeds. Something invisible must be providing the extra gravitational glue. That something is dark matter. The evidence for dark matter is overwhelming. In the 1970s, astronomer Vera Rubin was studying the rotation curves of spiral galaxies. She expected to find that stars farther from the galactic center would orbit more slowly, just like planets in our solar system. Instead, she discovered that stars at the galaxy's edge were moving just as fast as those closer to the center. This observation violated everything we knew about gravity and orbital mechanics. Unless, of course, there was 5 to 10 times more mass in each galaxy than we could see. But the most compelling evidence came from something called the Bullet Cluster. About 3.8 billion light-years from Earth, 2 massive galaxy clusters collided in one of the most violent events in the universe. When astronomers studied the aftermath, they found something extraordinary. The hot gas from both clusters, which we can detect through X-ray telescopes, had slowed down and separated during the collision. But the majority of the mass, detected through gravitational lensing, had sailed right through unimpeded. This created a clear spatial separation between where the normal matter ended up and where the gravitational effects were strongest. It was like watching 2 crowds of people collide, with most people getting tangled up and slowing down, while invisible ghosts walked straight through the chaos unaffected. This observation provided some of the most direct evidence that dark matter exists as a separate component from normal matter. What makes dark matter so mysterious is how it interacts with the universe. It doesn't absorb, emit, or reflect light. It doesn't interact with the electromagnetic force at all. As far as we can tell, dark matter only responds to gravity. It's like having a substance that can feel the pull of massive objects, but is completely invisible to every other force in nature. Scientists have proposed several candidates for what dark matter particles might be. The leading theory suggests they're something called WIMPs, which stands for Weakly Interacting Massive Particles. These theoretical particles would rarely interact with normal matter, explaining why we haven't detected them directly despite decades of searching. Deep underground laboratories around the world are running experiments to catch just one dark matter particle interacting with normal matter. But so far, these elusive particles have remained hidden. Another possibility involves particles called axions, which would be incredibly light and low energy. These theoretical particles were first proposed to solve a fundamental problem in particle physics, but they might also account for dark matter. Some scientists think dark matter could be composed of primordial black holes, ancient black holes formed in the early universe that are too small to detect directly but massive enough to provide the missing gravitational effects. What's fascinating is that dark matter appears to form the scaffolding of the entire universe. Computer simulations show that after the Big Bang, dark matter clumped together into vast filamentary structures, creating a cosmic web that spans billions of light-years. Normal matter then fell into the gravitational wells created by this dark matter framework, eventually forming the galaxies and galaxy clusters we see today. Think of it like this. Dark matter built the invisible skeleton of the universe, and everything we can see, every star, planet, and galaxy, formed along the bones of this cosmic skeleton. Without dark matter, the universe would look completely different. Galaxies might never have formed at all, or they might have formed much later and in completely different configurations. But dark matter is just the beginning of space's hidden contents. The next component is even stranger, and it makes up the largest portion of everything that exists: dark energy. While dark matter pulls things together through gravity, dark energy does the exact opposite. It's driving the universe apart, causing space itself to expand at an accelerating rate. The discovery of dark energy came as a complete shock to astronomers in the 1990s. 2 teams of researchers were studying distant supernovas to measure how the universe's expansion was slowing down over time. They expected to find that gravity was gradually winning, pulling everything back together after the initial Big Bang explosion. Instead, they found the opposite. The expansion was speeding up. This discovery was so unexpected that both teams double and triple checked their results. They analysed dozens of distant supernovas, each one serving as a standard candle to measure cosmic distances. The conclusion was inescapable. Something was counteracting gravity on the largest scales, pushing the fabric of space apart with ever-increasing force. Dark energy now accounts for approximately 68% of all energy and matter in the universe. 68%. That means more than 2/3 of reality consists of this mysterious force that we barely understand. Unlike dark matter, which clumps together and helps build cosmic structure, dark energy appears to be smoothly distributed throughout space, maintaining a constant density even as the universe expands. The leading theory for dark energy involves something called the cosmological constant, an idea that Einstein originally introduced and later abandoned. According to this theory, dark energy represents the energy of empty space itself. Every cubic centimeter of vacuum contains a tiny amount of energy that pushes outward, causing space to expand. As the universe grows larger, more space comes into existence, bringing more dark energy with it, which drives even faster expansion. But here's where it gets really weird. When physicists try to calculate how much energy empty space should contain based on quantum mechanics, they get an answer that's wrong by more than 100 orders of magnitude. That's not just a little bit wrong. That's spectacularly, embarrassingly wrong. It's like predicting someone weighs 1 pound and finding out they actually weigh more than all the galaxies in the observable universe combined. This enormous discrepancy between theory and observation represents one of the biggest unsolved problems in physics. Either our understanding of quantum mechanics is fundamentally flawed, or dark energy operates through mechanisms we haven't discovered yet. Some scientists propose that dark energy isn't constant, but changes over time through something called quintessence, a dynamic field that pervades space. Others suggest we need entirely new physics to explain what's happening. What makes dark energy so mind-bending is its implications for the future of the universe. If dark energy continues to accelerate cosmic expansion, eventually galaxies will be carried so far apart that they'll disappear beyond each other's horizons. Stars will burn out, black holes will evaporate through Hawking radiation, and the universe will end in a cold, empty, eternally expanding void. It's a scenario cosmologists call the Big Rip, where dark energy ultimately tears apart every structure in the universe, from galaxy clusters down to individual atoms. But space contains more than just dark matter and dark energy. Even in regions where these mysterious components dominate, the quantum vacuum itself seethes with constant activity. According to quantum mechanics, empty space isn't actually empty. It's filled with quantum fields that fluctuate wildly at the smallest scales, creating virtual particles that pop into existence and disappear faster than we can detect them. These quantum fluctuations represent one of the most bizarre aspects of what space is actually made of. The Heisenberg uncertainty principle tells us that energy and time are connected in a fundamental way. For incredibly brief moments, the universe can borrow energy from nowhere, create pairs of particles and antiparticles, and then those particles must annihilate each other before the cosmic debt comes due. It's like the universe has a credit card with an infinitely short payment period. What's remarkable is that these virtual particles aren't just theoretical constructs dreamed up by physicists with too much time on their hands. They have real measurable effects on the world around us. One of the most famous demonstrations involves something called the Casimir effect. If you take two perfectly flat metal plates and place them incredibly close together in a vacuum, they'll be pushed toward each other by an invisible force. Here's what's happening. Outside the plates, virtual particles of all possible wavelengths are constantly appearing and disappearing. But between the plates, Only virtual particles with specific wavelengths that fit perfectly in the gap can exist. This creates an imbalance in the quantum vacuum pressure, literally pushing the plates together with a force we can measure in the laboratory. Think about that for a moment. Empty space contains so much hidden activity that it can physically move objects in our everyday world. The vacuum itself has structure, energy, and the ability to influence matter. When physicists first calculated this effect in the 1940s, many thought it was impossible. But experiments have confirmed it repeatedly. The quantum vacuum is real, and it's everywhere. These quantum fluctuations also play a crucial role in the cosmic microwave background radiation that fills all of space. This ancient light, released when the universe first became transparent about 380,000 years after the Big Bang, carries the fossil imprint of quantum fluctuations that existed in the earliest moments of cosmic history. Those tiny quantum variations, stretched to enormous scales during cosmic inflation, became the seeds for every galaxy, star, and planet that exists today. The cosmic microwave background represents another major component of what space is made of. Every cubic centimeter of the universe contains about 400 photons of this ancient radiation, cooled by cosmic expansion to just under 3 degrees above absolute zero. You can't see these photons with your eyes, but they're there, streaming through your body at this very moment, carrying information about the universe when it was less than 1% of its current age. But space also contains more familiar forms of matter and energy that we often overlook. Electromagnetic fields permeate every corner of the cosmos, generated by stars, planets, galaxies, and even the quantum vacuum itself. These fields create invisible highways and barriers for charged particles, shaping the flow of cosmic rays and solar wind throughout the universe. Our own solar system sits inside a vast bubble called the heliosphere, carved out by the solar wind as it pushes against the interstellar medium. This wind consists of charged particles streaming away from the sun at over 1 million miles per hour, carrying the sun's magnetic field throughout the solar system. When this wind encounters Earth's magnetic field, it creates our planet's magnetosphere, a magnetic bubble that protects us from most cosmic radiation. The space between stars isn't empty either. The interstellar medium contains roughly 1 atom per cubic centimeter, along with dust grains, magnetic fields, and various forms of radiation. That might sound like nothing, but across the vast distances between stars, this tenuous material adds up to significant amounts of mass. In fact, the interstellar medium in our galaxy contains enough material to form millions of new stars. Different regions of space have wildly different compositions and properties. Near massive stars, space is filled with intense radiation and stellar winds that can strip electrons from atoms across entire star systems. In the centers of galaxies, supermassive black holes create jets of plasma that extend for millions of light years, heating and ionizing the surrounding medium. In galaxy clusters, space is filled with hot plasma at temperatures of millions of degrees, visible only through X-ray telescopes. Even the space between galaxy clusters isn't truly empty. The intergalactic medium contains a warm hot plasma with temperatures around 100,000 to 10 million degrees, left over from cosmic structure formation. This plasma is so diffuse that it's almost impossible to detect directly, but it may contain up to half of all normal matter in the universe. What's becoming clear is that space exists in a hierarchy of environments, each with its own unique composition and behavior. The quantum vacuum provides the fundamental background, with its seething virtual particles and zero-point energy. Dark matter creates the gravitational scaffolding that shapes cosmic structure on the largest scales. Dark energy drives the overall expansion and evolution of space itself. On top of this foundation, electromagnetic fields create complex networks of force that guide the motion of charged particles. Plasma of various temperatures and densities fills different regions, from the hot coronas around stars to the warm, hot intergalactic medium. Radiation of all wavelengths streams through space, from radio waves generated by distant galaxies to gamma rays produced by the most violent events in the universe. But perhaps most importantly, space itself has properties and behaviors that we're only beginning to understand. Einstein showed us that space and time are woven together into a single fabric called space-time, and that massive objects actually warp and bend this fabric. What we experience as gravity is really just the curvature of space-time caused by mass and energy. This means that space isn't just a passive container holding the universe's contents. Space is dynamic, flexible, and responsive. It can be stretched, compressed, twisted, and even torn under extreme conditions. Black holes create such intense curvature that they punch holes in space-time itself. Gravitational waves, created by accelerating masses, send ripples through the fabric of space that we can now detect with incredible precision. The discovery of gravitational waves opened an entirely new window into the nature of space. When two black holes spiral into each other and merge, they create distortions in space-time that travel outward at the speed of light. These waves are so subtle that they change the length of kilometer-long laser interferometers by less than 1/10,000th the width of a proton. Yet we can measure these tiny distortions, proving that space itself can vibrate like a drumhead. Even more exotic possibilities exist at the frontiers of physics. Some theories suggest that space might be quantized at the smallest scales, made up of discrete units smaller than anything we can currently measure. Other theories propose that our three-dimensional space might actually be a projection of information encoded on a two-dimensional surface, like a cosmic hologram. String theory suggests that the fundamental building blocks of reality aren't particles at all, but tiny vibrating strings existing in 10 or 11 dimensions. Most of these extra dimensions would be compactified or hidden from our everyday experience, but they might still influence the properties of the space we can observe. What's remarkable is how all these different components of space work together to create the universe we see around us. Dark matter provides the gravitational framework that allows galaxies to form. Dark energy drives the expansion that prevents the universe from collapsing back in on itself. Quantum fluctuations in the early universe created the density variations that eventually became stars and planets. The cosmic microwave background provides the thermal bath that sets the temperature of deep space. Electromagnetic fields channel energy and particles across vast distances, connecting events separated by billions of light years. The interstellar and intergalactic medium provide the raw materials for new generations of stars and galaxies, and space-time itself provides the stage where all these cosmic dramas unfold, bending and flexing in response to the mass and energy it contains. As we push deeper into the 21st century, our understanding of space continues to evolve. New telescopes are revealing previously hidden components of the cosmic web. Particle accelerators are probing the quantum properties of vacuum itself. Gravitational wave detectors are opening new channels of information about the dynamic nature of space-time. We're discovering that space is far from empty, far from passive, and far more complex than our ancestors could have imagined. Every cubic centimeter contains layers upon layers of fields, particles, radiation, and forces, all interacting in ways that span the range from quantum mechanics to cosmic evolution. What we're starting to realize is that space operates on principles that challenge our most basic assumptions about reality. Take the concept of information, for instance. Recent discoveries suggest that space itself might be a carrier of information in ways we never imagined. When matter falls into a black hole, physicists once thought that information was destroyed forever, violating one of the fundamental laws of physics. But new theories propose that this information is actually encoded on the black hole's event horizon, suggesting that the surface of space-time can store vast amounts of data. This leads us to one of the most mind-bending ideas in modern physics. The holographic principle suggests that all the information contained in a volume of space can be encoded on its boundary, like a three-dimensional hologram projected from a two-dimensional surface. If this is true, then the space around you right now might be a projection of information stored somewhere else entirely. Your entire reality could be a cosmic hologram, and space itself might be the medium through which this information is transmitted and processed. But let's bring this back down to scales we can wrap our heads around. Even in the seemingly empty space of our solar system, there's constant activity that affects our daily lives. Solar wind particles stream past Earth at incredible speeds, carrying magnetic field lines that can disrupt our satellite communications and create the beautiful auroras we see at the poles. This isn't just pretty light shows, it's evidence that space around our planet is filled with charged particles and electromagnetic fields that interact with our technology. The space around Earth is also littered with human-made debris. Millions of pieces of space junk orbit our planet, from defunct satellites to paint flecks from rocket launches. This orbital debris creates its own ecosystem of objects moving at incredible speeds, sometimes colliding and creating even more fragments. In a very real sense, we've polluted the space immediately around our planet with the byproducts of our technological civilization. Beyond our solar system, the interstellar medium reveals even more complexity. This sparse material between stars contains not just individual atoms and molecules, but also complex organic compounds that might be the building blocks of life. Polycyclic aromatic hydrocarbons, amino acids, and even simple sugars have been detected in the space between stars. This suggests that the basic chemistry of life might be happening throughout the galaxy, in regions we once considered sterile and empty. Stellar nurseries represent some of the most active regions of space, where gravity pulls together the interstellar medium to form new stars and planetary systems. These regions are filled with hot gas, dust clouds, and intense radiation from newly formed stars. The Eagle Nebula, the Orion Nebula, and countless other star-forming regions show us that space can be a violent, chaotic environment where matter is constantly being recycled and transformed. When massive stars reach the end of their lives, they explode as supernovas, injecting enormous amounts of energy and heavy elements into the surrounding space. These explosions create shockwaves that travel through the interstellar medium for thousands of years, heating gas, triggering new star formation, and distributing the elements necessary for rocky planets and life itself. The calcium in your bones, the iron in your blood, and the oxygen you breathe were all forged in the cores of massive stars and scattered through space by these cosmic explosions. Neutron stars, the ultra-dense remnants of some supernovas, create some of the most extreme environments in the universe. These objects pack more mass than our Sun into a sphere just 12 miles across, creating gravitational fields so intense that they warp space-time in measurable ways. The space around neutron stars is filled with powerful magnetic fields, trillions of times stronger than Earth's, accelerating particles to near light speed and creating beams of radiation that sweep across space like cosmic lighthouses. Pulsars, rapidly spinning neutron stars, send out precisely timed radio pulses that astronomers use as cosmic clocks. These pulses are so regular that they rival atomic clocks in their precision, and tiny variations in their timing can reveal the presence of gravitational waves passing through space. In essence, pulsars turn the entire galaxy into a gravitational wave detector, using the fabric of space itself as the measuring instrument. Black holes represent the ultimate extreme in space's behavior. Near the event horizon of a stellar mass black hole, space-time is so severely warped that time itself slows to a crawl relative to distant observers. An astronaut falling toward a black hole would appear frozen at the event horizon to outside observers, while from the astronaut's perspective, they would continue falling normally. This isn't science fiction. It's a direct consequence of Einstein's general relativity, confirmed by decades of observation and mathematical analysis. Supermassive black holes at the centers of galaxies create even more dramatic effects on the surrounding space. These monsters, containing millions or billions of times the mass of our Sun, generate accretion disks of superheated material that can outshine entire galaxies. The space around these black holes is filled with jets of plasma moving at significant fractions of light speed, creating structures that extend for millions of light years. The supermassive black hole at the center of our own galaxy, Sagittarius A star, has been directly imaged by the Event Horizon Telescope, showing the shadow it casts against the glowing material surrounding it. This achievement required coordinating radio telescopes around the world to create an Earth-sized detector, demonstrating how space itself can be used as a lens to magnify distant objects. Galaxy clusters, the largest gravitationally bound structures in the universe, reveal space on its grandest scales. These collections of hundreds or thousands of galaxies are embedded in vast halos of dark matter and filled with hot plasma at temperatures of tens of millions of degrees. The space between galaxies in these clusters is anything but empty, containing enough hot gas to outweigh all the stars in all the galaxies combined. When galaxy clusters collide, they create some of the most energetic events since the Big Bang. These cosmic crashes heat plasma to hundreds of millions of degrees and accelerate particles to incredible energies. Radio telescopes reveal vast shock fronts and turbulent magnetic fields created by these collisions, showing that space can be a battlefield where invisible forces clash on scales spanning millions of light years. The cosmic web itself, the largest scale structure in the universe, demonstrates how space organizes matter and energy across billions of light years. Dark matter filaments stretch between galaxy clusters like a vast scaffolding, channeling gas and galaxies along their length. The space between these filaments, called cosmic voids, represents some of the emptiest regions in the universe, yet even these contain sparse populations of galaxies and dark matter. Recent observations have detected a warm-hot intergalactic medium filling the space between galaxies, possibly containing up to half of all the normal matter in the universe. This plasma is so diffuse and at such specific temperatures that it's nearly invisible to most telescopes, yet it may represent a major component of cosmic matter that we're only beginning to understand. Cosmic rays, high-energy particles, accelerated by violent cosmic events, stream through space in all directions. These particles, mostly protons and heavier atomic nuclei, carry energies millions of times higher than anything we can create in particle accelerators on Earth. When they strike our atmosphere, they create showers of secondary particles that rain down on the surface. Some cosmic rays are so energetic that their source remains a mystery, suggesting there are processes operating in space that we haven't yet discovered. The cosmic neutrino background represents another component of space that's almost entirely invisible to us. These ghostly particles, produced in the early universe and by various cosmic processes, stream through space at nearly the speed of light. Trillions of them pass through your body every second without interacting with a single atom. Detecting these neutrinos requires massive underground detectors filled with thousands of tons of ultra-pure water or ice. Yet they carry unique information about cosmic events that no other messenger can provide. Primordial gravitational waves, if they exist, would represent the earliest signature we could ever hope to detect from the universe's birth. These ripples in space-time, generated during cosmic inflation in the first fraction of a second after the Big Bang, would be stretched to enormous wavelengths by the expansion of the universe. Detecting them would require space-based gravitational wave observatories with laser arms millions of miles long, turning the solar system itself into a detector for these ancient echoes. The quantum vacuum continues to surprise us with new phenomena. Recent experiments have shown that intense electromagnetic fields can actually create particle-antiparticle pairs from the vacuum itself, confirming that empty space contains latent energy that can be converted into matter under extreme conditions. Other experiments probe whether the vacuum might have a preferred direction or handedness, which could reveal new physics beyond our current understanding. Virtual particles in the quantum vacuum might also play a role in cosmic evolution. Some theories suggest that quantum fluctuations in the early universe could have influenced the formation of dark matter, or even created the dark energy that drives cosmic acceleration. The boundary between quantum mechanics and cosmology continues to blur as we discover connections between the smallest and largest scales in nature. Space-based observatories have revealed that the universe is filled with backgrounds of radiation at every wavelength, from radio waves to gamma rays. Each of these backgrounds tells a different story about cosmic history and the processes operating throughout space. The cosmic X-ray background reveals the combined emission from millions of black holes and other high-energy sources. The cosmic gamma-ray background includes contributions from dark matter annihilation, if it occurs, potentially providing our first direct detection of dark matter particles. Even the expansion of space itself raises profound questions about what space actually is. As dark energy drives cosmic acceleration, new space is constantly being created between distant galaxies. This isn't like stretching a rubber sheet, where the material becomes thinner as it expands. Instead, the density of dark energy remains constant even as space expands, meaning that more dark energy comes into existence as more space is created. This suggests that space and energy are connected in ways that challenge our basic understanding of conservation laws. The concept of space-time foam, proposed by physicist John Wheeler, suggests that at the smallest scales, space and time themselves might be quantized and constantly fluctuating. At distances smaller than the Planck length, about 10 to the negative 35th meters, space-time might be a seething foam of virtual black holes and wormholes, constantly appearing and disappearing, faster than any conceivable measurement could detect them. This quantum geometry could be the fundamental foundation from which our smooth, continuous space-time emerges. Wormholes, though purely theoretical, represent another way that space might be far stranger than it appears. These hypothetical tunnels through space-time could connect distant regions of the universe, or even different universes entirely. While no wormholes have ever been detected, they're consistent with Einstein's equations under certain exotic conditions. If they exist, they would represent shortcuts through space that could fundamentally change our understanding of cosmic distances and causality. The possibility of extra dimensions adds yet another layer of complexity to space's true nature. String theory and other advanced physics models suggest that our familiar 3 dimensions of space might be just a subset of a higher dimensional reality. These extra dimensions could be compactified or curled up so small that we can't detect them directly, yet they might influence the forces and particles we observe in our 3-dimensional world. Recent experiments at particle accelerators have searched for evidence of these extra dimensions by looking for particles that could escape into higher dimensional space. While no definitive evidence has been found, the possibility remains that space extends far beyond the three dimensions we experience, with profound implications for our understanding of gravity, quantum mechanics, and the fundamental structure of reality. Dark matter interactions represent another frontier in understanding space's hidden components. While dark matter doesn't interact electromagnetically, it might interact through other forces we haven't discovered yet. Some theories propose a rich dark sector with its own dark photons, dark atoms, and even dark chemistry. If this hidden universe exists, it could be operating in parallel to our own, sharing the same space, but remaining almost entirely invisible to us. The search for dark matter continues, with increasingly sophisticated detectors buried deep underground to shield them from cosmic rays and other background radiation. These experiments look for the tiny recoil when a dark matter particle collides with an atomic nucleus, an event so rare that detectors must monitor tons of target material for years to have a chance of seeing a single interaction. Direct detection of dark energy remains even more challenging because it doesn't clump like dark matter, but instead maintains a constant density throughout space. Understanding dark energy may require entirely new theoretical frameworks that go beyond our current models of quantum field theory and general relativity. The cosmic microwave background continues to provide our most detailed information about the early universe and the fundamental parameters that govern cosmic evolution. Tiny temperature variations in this ancient light, measured to incredible precision by space-based telescopes, reveal the initial conditions that led to everything we see today. These observations have confirmed that space is flat on the larger scales, meaning that parallel lines will never meet, no matter how far they're extended. This geometric flatness of space has profound implications for cosmic evolution and the ultimate fate of the universe. If space were curved like the surface of a sphere, the universe might eventually stop expanding and collapse back on itself. If it were curved like a saddle, it would expand forever, but at an ever-decreasing rate. The fact that space appears to be perfectly flat suggests a delicate balance between these extremes, possibly indicating that cosmic inflation stretched space so much that any original curvature was erased. The relationship between space, time, and consciousness represents one of the deepest mysteries in science. Quantum mechanics suggests that the act of measurement or observation can influence the behavior of particles, leading some physicists to wonder whether consciousness plays a fundamental role in shaping reality. While this remains highly speculative, it raises profound questions about whether space exists independently of observers, or whether it's somehow dependent on conscious awareness. As we continue to probe deeper into the nature of space, we're discovering that it's far more complex, dynamic, and mysterious than we ever imagined. Every cubic centimeter contains layers of fields, particles, and forces operating on scales from the quantum to the cosmic. Space isn't just the stage where the cosmic drama unfolds. It's an active participant in every scene, shaping the behavior of matter and energy across the entire observable universe. The implications of this cosmic complexity become even more staggering when we consider how space behaves during extreme events. Take gamma-ray bursts, the most powerful explosions in the universe since the Big Bang. When a massive star collapses into a black hole, or when two neutron stars merge, they release more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. These events don't just happen in space. They fundamentally alter the properties of space itself. During a gamma-ray burst, the intense radiation and particle acceleration create shockwaves that propagate through the surrounding medium at significant fractions of light speed. The space around these events becomes a cauldron of high-energy physics. where photons can spontaneously convert into particle-antiparticle pairs, and where magnetic fields become so intense they twist the fabric of space-time itself. We're talking about regions where the normal rules of physics are pushed to their absolute limits. But here's what's truly mind-blowing about space. Even in the quietest, most remote regions between galaxy superclusters, far from any stars or active galactic nuclei, space is still buzzing with activity that would make your head spin. The zero-point energy of the quantum vacuum means that even at absolute zero temperature, space contains irreducible quantum fluctuations that can never be eliminated. These fluctuations aren't just theoretical curiosities. They influence the behavior of atoms, the stability of matter, and even the rate at which particles decay. The Lamb shift in hydrogen atoms, first observed in the 1940s, showed that the energy levels of electrons are slightly different from what basic quantum mechanics predicted. This tiny difference comes from the electron's interaction with virtual photons in the quantum vacuum, proving that empty space has measurable effects on the atoms that make up your body. The Casimir effect, which we touched on earlier, reveals even more bizarre properties of the quantum vacuum. Not only can it create attractive forces between metal plates, but under certain conditions, it can create repulsive forces as well. Researchers have designed geometries where the Casimir effect actually pushes objects apart, suggesting that the quantum vacuum could theoretically be used for propulsion or to create materials with exotic mechanical properties. Some physicists have even speculated about whether the quantum vacuum could be a source of energy. After all, if every cubic centimeter of space contains zero-point energy, could we somehow tap into this vast reservoir? Unfortunately, the laws of thermodynamics seem to forbid extracting usable energy from the vacuum state. But the very fact that we're asking these questions shows how far our understanding of space has evolved. The cosmic neutrino background adds another layer of hidden activity to space. These particles, produced in the first few seconds after the Big Bang, have been streaming freely through the universe for nearly 14 billion years. Unlike photons, which interact readily with matter, neutrinos barely interact with anything. They can pass through entire planets without hitting a single atom, yet they carry information about the early universe that we can't get any other way. Detecting these relic neutrinos requires detectors of almost unimaginable sensitivity. The proposed Ptolemy experiment aims to detect cosmic neutrinos by observing their effect on tritium atoms in a carefully controlled environment. If successful, it would open a new window into the universe's first moments, revealing conditions when the cosmos was less than 1 second old. The interplay between all these components of space creates a dynamic, ever-changing environment that operates on multiple scales simultaneously. Consider what happens when a supernova explodes in a distant galaxy. The initial explosion sends shock waves through the local interstellar medium, heating gas to millions of degrees and accelerating particles to incredible energies. These cosmic rays then stream through space for millions of years, eventually reaching Earth and other distant locations. But the supernova also produces gravitational waves that ripple through space-time at the speed of light. These waves carry information about the collision in a completely different form than electromagnetic radiation or particles. When they pass through our solar system, they stretch and compress space itself by amounts smaller than 1,000th the width of a proton. Yet our gravitational wave detectors can measure these tiny distortions, revealing details about the explosion that no other method could provide. Meanwhile, the heavy elements forged in the star's core are dispersed throughout space, enriching the interstellar medium with carbon, oxygen, silicon, and iron. These elements will eventually be incorporated into new generations of stars and planets, carrying the chemical signature of that ancient explosion billions of years into the future. In this way, Space serves as both a transport medium and a memory bank, preserving information about cosmic events across vast spans of time. The magnetic fields that thread through space add another dimension of complexity. These fields, generated by rotating charged objects like stars and planets, extend far beyond their sources and interact with each other in intricate ways. The Sun's magnetic field, carried outward by the solar wind, fills our entire solar system and creates a boundary called the heliopause, where it meets the interstellar magnetic field. This interaction creates turbulent regions where magnetic field lines reconnect and release stored energy in explosive events. Similar processes occur throughout the galaxy, from the magnetospheres of planets to the accretion disks around black holes. Magnetic reconnection events can accelerate particles to incredible energies and trigger phenomena ranging from solar flares to the powerful jets observed emanating from active galactic nuclei. The cosmic web itself represents perhaps the most impressive demonstration of how space organizes matter and energy on the largest scales. This vast network of dark matter filaments, stretching across billions of light years, channels the flow of gas and galaxies throughout the universe. Computer simulations show that this structure emerged naturally from tiny quantum fluctuations in the early universe, amplified by gravity over billions of years of cosmic evolution. Along these filaments, gas flows like water through cosmic rivers, feeding the formation of new stars and galaxies. Where filaments intersect, massive galaxy clusters form, containing thousands of individual galaxies bound together by gravity. The space between these filaments, the cosmic voids, represents some of the largest empty regions in the universe, yet even they contain sparse populations of galaxies and dark matter. Recent observations have revealed that these cosmic voids aren't completely empty. They contain a network of smaller filaments and walls, creating a hierarchy of structures within structures. Some voids span hundreds of millions of light years, so large that light from one side takes longer to reach the other side than the entire age of the universe when the first stars formed. The expansion of space itself continues to be one of the most profound aspects of cosmic evolution. Unlike the explosion of a bomb, where debris flies outward into pre-existing space, the Big Bang created space itself. There was no center to the explosion and no edge to the expanding material. Instead, every point in space is expanding away from every other point, creating the illusion that we're at the center of the universe when viewed from any location. This expansion affects different regions of space differently. On small scales, where gravity dominates, space doesn't expand at all. Your body, the Earth, our solar system, and even our entire galaxy maintain their sizes despite cosmic expansion. It's only on scales larger than galaxy clusters that the expansion becomes noticeable. And it's only on the largest scales that dark energy's influence becomes dominant. The rate of expansion isn't constant either. During the first fraction of a second after the Big Bang, space expanded exponentially during a period called cosmic inflation. This brief but dramatic expansion stretched quantum fluctuations to cosmic scales, creating the density variations that would eventually become galaxies and stars. After inflation ended, the expansion slowed down as gravity fought against it, until about 5 billion years ago, when dark energy began to dominate and cosmic expansion started accelerating again. This acceleration means that distant galaxies are moving away from us at ever-increasing speeds. Galaxies more than about 15 billion light-years away are receding faster than the speed of light. This doesn't violate relativity because the galaxies themselves aren't moving through space faster than light. Rather, the space between us and them is expanding so rapidly that the recession velocity exceeds light speed. The cosmic event horizon represents the ultimate boundary of observable space. Light from galaxies beyond this horizon can never reach us because space is expanding too rapidly. As time passes, this horizon will actually shrink, cutting us off from an ever larger fraction of the universe. Eventually, only our local group of galaxies will remain visible, with everything else disappearing beyond the cosmic horizon. But even within our observable universe, space contains regions that remain fundamentally unknowable. The interior of black holes represents a boundary beyond which information cannot escape. Once matter crosses the event horizon, it enters a region of space-time so severely curved that all paths lead inexorably toward the central singularity. The space inside a black hole might connect to other regions of space-time through wormholes, or it might simply end at the singularity where the laws of physics break down. Hawking radiation adds another twist to our understanding of black hole space-time. According to quantum mechanics, black holes should slowly evaporate by emitting particles created near their event horizons. This process converts the black hole's mass into radiation, eventually causing even the most massive black holes to disappear entirely. The space around evaporating black holes becomes filled with Hawking radiation, carrying away the black hole's information content, though exactly how this information is encoded remains one of physics' greatest unsolved problems. The holographic principle suggests that all the information that falls into a black hole is actually encoded on its event horizon, like a two-dimensional hologram that contains three-dimensional information. If this is correct, then the space inside the black hole might be entirely illusory, with the real degrees of freedom living on the boundary. This idea has been extended to suggest that our entire universe might be holographic, with the three-dimensional space we experience being a projection of information stored on a two-dimensional surface. String theory pushes these ideas even further, proposing that the fundamental building blocks of reality aren't particles, but tiny vibrating strings existing in 10 or 11 dimensions. Most of these extra dimensions would be compactified so small that we can't detect them directly, but they would still influence the properties of particles and forces in our familiar three-dimensional space. In string theory, even the concept of space itself becomes emergent rather than fundamental. Space and time might arise from more basic quantum entanglement between the underlying string degrees of freedom. This suggests that the space we experience is like the surface of a deep ocean, with vast realms of quantum information processing happening at deeper levels that we can't directly access. Loop quantum gravity offers an alternative approach, suggesting that space itself is quantized at the Planck scale. In this theory, space is made up of discrete units, like a cosmic mesh or foam, with a minimum possible size of about 10 to the negative 35th meters. At these scales, the smooth geometry of Einstein's spacetime would break down into a granular structure where the concepts of distance and direction lose their meaning. The implications of quantized space are profound. It could resolve the paradoxes that arise when quantum mechanics meets general relativity, providing a framework for understanding what happens at the center of black holes or during the first moments of the Big Bang. It might also explain why space appears smooth on large scales, despite being fundamentally granular at the smallest scales. Recent advances in quantum information theory have revealed deep connections between space, time, and information processing. The ADS/CFT correspondence, one of the most important discoveries in theoretical physics, shows that gravity in a higher dimensional space can be exactly equivalent to quantum field theory on its lower dimensional boundary. This suggests that space-time might be an emergent phenomenon arising from quantum entanglement between more fundamental degrees of freedom. These ideas are revolutionizing our understanding of what space actually is. Rather than being a passive arena where physics happens, space might be an active information processing system, constantly computing the quantum correlations that give rise to our experience of reality. The geometry of space-time could emerge from the pattern of quantum entanglement between different regions, with gravity itself being a manifestation of information geometry. As we push deeper into the 21st century, our tools for studying space continue to evolve at a breathtaking pace. The James Webb Space Telescope is revealing the earliest galaxies that formed when the universe was less than 5% of its current age, showing us how space looked when it was filled with the first generation of stars and black holes. These observations are rewriting our understanding of how cosmic structure emerged from the primordial quantum fluctuations. Gravitational wave astronomy has opened an entirely new window into space's dynamic behavior. The LIGO and Virgo detectors have observed dozens of black hole and neutron star mergers, revealing a universe filled with these violent events. Future space-based gravitational wave observatories will detect mergers of supermassive black holes, probe the structure of space-time near these extreme objects, and potentially observe gravitational waves from cosmic inflation itself. Dark matter detection experiments continue to push the boundaries of sensitivity, searching for the elusive particles that make up more than a quarter of all reality. These experiments use everything from underground tanks of liquid xenon to miles-long particle accelerators, attempting to catch dark matter in the act of interacting with normal matter. The discovery of dark matter particles would revolutionize our understanding of what space contains and how it evolved. Quantum experiments are probing the vacuum itself with unprecedented precision, testing whether space-time has a preferred direction, whether virtual particles behave exactly as theory predicts, and whether new physics emerges at high-energy scales. Some experiments search for axions, hypothetical particles, that could make up dark matter and might be detectable through their interaction with strong magnetic fields. Others look for signs that space has additional dimensions or that the vacuum has structure we haven't yet discovered. The search for life beyond Earth is also reshaping our understanding of space as a potentially life-bearing environment. The discovery of thousands of exoplanets has revealed that planetary systems are common throughout the galaxy, with many planets existing in the habitable zones around their stars where liquid water could exist. The space between stars might also harbour life, with organisms surviving in the interstellar medium or on rogue planets ejected from their parent systems. Even our solar system continues to surprise us with new discoveries about the nature of space. The Voyager spacecraft, now in interstellar space, are sending back data about conditions beyond the heliopause where the solar wind meets the interstellar medium. This boundary region is more complex and dynamic than expected, with magnetic field reversals, particle acceleration, and other phenomena that reveal how different regions of space interact. The space around Earth itself is becoming increasingly important as humanity expands its presence beyond our planet. The near-Earth environment is filled with satellites, space debris, and the International Space Station, creating a new ecosystem of human technology in space. Understanding how this environment behaves, from radiation effects on electronics to the dynamics of orbital mechanics, is crucial for future space exploration and development. Looking toward the future, our understanding of space will continue to evolve as we develop new technologies and theoretical frameworks. Quantum computers might allow us to simulate cosmic evolution with unprecedented detail, revealing how quantum mechanics and gravity work together to create the large-scale structure of the universe. Artificial intelligence could help us identify patterns in cosmic data that human researchers might miss, potentially revealing new components of space that we haven't yet imagined. The possibility of detecting primordial gravitational waves from cosmic inflation would provide direct evidence for the quantum origin of cosmic structure, confirming that the largest structures in the universe grew from quantum fluctuations smaller than atomic nuclei. Such a detection would validate our understanding of space's quantum foundations and might reveal new physics operating during the universe's first moments. As we stand on the threshold of these discoveries, one thing becomes clear. Space is not the empty, passive void our ancestors imagined. It's a complex, dynamic, multi-layered environment that operates according to principles we're only beginning to understand. Every cubic centimeter contains quantum fields, virtual particles, dark matter, dark energy, electromagnetic radiation, and gravitational effects that span the range from local to cosmic scales. The space around you right now is filled with cosmic microwave background photons from the early universe, neutrinos from the Big Bang and stellar cores, dark matter particles streaming through the Earth, virtual particles popping in and out of existence, gravitational waves from distant black hole mergers, and electromagnetic fields from sources throughout the galaxy. You're not sitting in empty space. You're immersed in a rich, invisible ocean of cosmic activity that connects you to the largest and smallest scales of reality. This realization fundamentally changes how we think about our place in the universe. We're not isolated beings living on a tiny planet surrounded by empty void. We're integral parts of a vast, interconnected cosmic web where every particle in our bodies was forged in the cores of ancient stars, where the quantum vacuum around us seethes with virtual particles, and where the expansion of space itself carries us along on a journey that began nearly 14 billion years ago. The story of space is still being written, with each new discovery revealing additional layers of complexity and beauty. From the quantum foam at the smallest scales to the cosmic web spanning billions of light years, space emerges as the most sophisticated, dynamic, and mysterious environment we've ever encountered. And the most remarkable thing is that we're just getting started in our quest to understand what space is actually made of. What makes this even more fascinating is how space behaves during the most extreme events we can observe. When two black holes spiral toward each other in their final death dance, they don't just create gravitational waves. They actually stretch and compress the fabric of space-time so violently that the geometry of space itself becomes distorted in ways that challenge our basic understanding of reality. Picture this scenario. As these massive objects accelerate around each other at significant fractions of light speed, they create ripples in space-time that propagate outward like waves on a cosmic ocean. But these aren't gentle ripples. We're talking about distortions so powerful they can be detected across billions of light years, yet so subtle they change distances by less than 1,000th the width of a proton. The LIGO detectors that measure these gravitational waves are essentially using the entire Earth as a reference frame to detect when space itself gets squeezed and stretched. Think about that for a moment. Space isn't just a stage where cosmic events unfold. It's an active participant that can be twisted, compressed, and made to vibrate like a cosmic drumhead. But here's where things get really wild. During the final moments before two black holes merge, the space around them becomes so warped that time itself behaves differently depending on where you're located. An observer far from the collision would see time passing normally, but an observer closer to the action would experience time dilation so extreme that seconds could stretch into hours relative to the distant observer. This isn't science fiction speculation. It's a direct consequence of Einstein's general relativity, confirmed by decades of observation. Space and time are so intimately connected that you can't distort one without affecting the other. When massive objects move through space, they drag the fabric of space-time along with them in an effect called frame dragging. The space around a spinning black hole actually rotates along with the black hole itself. Neutron stars reveal even more bizarre properties of space under extreme conditions. These ultra-dense objects pack more mass than our Sun into a sphere just 12 miles across. The gravitational field is so intense that it warps space to the point where the surface appears to curve back on itself. Light rays bend so dramatically that you could theoretically see the back of your own head if you stood on a neutron star's surface. The magnetic fields around neutron stars are equally mind-bending. We're talking about field strengths trillions of times more powerful than anything we can create on Earth. These fields are so intense, they actually affect the quantum vacuum itself, causing virtual particles to behave in ways that become observable. In the most extreme cases, the magnetic field can literally tear atoms apart by stretching their electron orbitals beyond the breaking point. Magnetars, the most magnetic objects known, create fields so powerful they would erase every credit card on Earth from a distance of halfway to the moon. The space around these objects becomes a laboratory for extreme physics, where the normal rules break down completely. Virtual photons in the quantum vacuum can be converted into real photons by the intense magnetic field, creating a ghostly glow that we can detect with X-ray telescopes. But let's zoom out from these cosmic extremes and consider how space behaves in more familiar environments. Even in our own solar system, space is far from uniform or static. The solar wind creates a dynamic bubble called the heliosphere that extends far beyond Pluto's orbit. This isn't just empty space with a few particles flying through it. It's a complex plasma environment where magnetic fields, shock waves, and particle acceleration create conditions that would be impossible to replicate in any laboratory on Earth. The boundary where the solar wind meets the interstellar medium, called the heliopause, represents a fundamental transition in the properties of space itself. Beyond this boundary, we enter the interstellar medium, where space has different temperature, density, and magnetic field properties. The Voyager spacecraft, now more than 14 billion miles from Earth, are sending back data from this alien environment, revealing that interstellar space has its own weather patterns and dynamics. Cosmic rays add another layer of activity to space throughout our galaxy. These high-energy particles, accelerated by supernova remnants and other violent events, stream through space in all directions at speeds approaching that of light. When they interact with magnetic fields in space, they create complex patterns of deflection and acceleration that turn the galaxy into a vast particle accelerator. Some cosmic rays carry so much energy that their origin remains a complete mystery. We're talking about individual particles with more kinetic energy than a Major League Baseball traveling at 60 miles per hour. These ultra-high energy cosmic rays challenge our understanding of what processes in space could possibly accelerate particles to such incredible energies. The fact that these particles exist tells us that space contains acceleration mechanisms far more powerful than anything we've imagined. Somewhere in the universe, possibly in the jets from supermassive black holes, or in the shock waves from gamma-ray bursts, space itself becomes a machine for creating the most energetic particles we've ever detected. Galaxy formation reveals how space organizes itself on the largest scales through processes we're only beginning to understand. Dark matter provides the gravitational scaffolding, but the details of how gas flows along dark matter filaments, cools, and condenses into stars involve complex physics operating across enormous ranges of scale and time. Computer simulations show that galaxy formation is an incredibly violent process. Gas streams crash into each other at speeds of hundreds of kilometers per second, creating shock waves that heat material to millions of degrees. Stars form in bursts of activity that can consume most of a galaxy's gas supply in just a few million years. Supermassive black holes grow alongside their host galaxies, regulating star formation through powerful jets and winds that can heat gas throughout the entire galaxy. The space between galaxies in clusters reveals even more dramatic physics. Hot plasma at temperatures of tens of millions of degrees fills the space between galaxies, outweighing all the stars in all the galaxies combined. This plasma is so hot that it glows brightly in X-rays, revealing intricate structures shaped by galaxy motions, magnetic fields, and the gravitational influence of dark matter. When galaxy clusters collide, they create some of the most energetic events since the Big Bang. These cosmic train wrecks heat plasma to hundreds of millions of degrees and generate shockwaves that span millions of light years. Radio telescopes reveal vast regions where particles are accelerated to incredible energies, creating diffuse emission that traces the history of these cosmic collisions. The Coma cluster, one of the nearest large galaxy clusters, shows us how space can be filled with invisible structure. Radio observations reveal a vast halo of relativistic electrons surrounding the entire cluster, evidence of particle acceleration processes operating on scales larger than anything in our local cosmic neighborhood. The space within this cluster is anything but empty. It's a cauldron of high-energy physics where magnetic fields, shock waves, and turbulent plasma create conditions that push the boundaries of our understanding. Dark matter's role in shaping space becomes even more mysterious when we consider how it might interact with itself. While dark matter doesn't respond to electromagnetic forces, it might have its own dark interactions that we haven't discovered yet. Some theories propose a rich dark sector with dark photons, dark atoms, and even dark chemistry operating in parallel to our familiar world. If dark matter can interact with itself, it could form complex structures invisible to our telescopes, but potentially detectable through their gravitational effects. Dark matter might clump into dense cores, form dark disks within galaxies, or even create dark planets and dark stars. These objects would share the same space as normal matter, but remain almost entirely hidden from view. The search for dark matter continues with increasingly sophisticated experiments buried deep underground to shield them from cosmic ray interference. These detectors look for the tiny recoil when a dark matter particle collides with an atomic nucleus, an event so rare that experiments must monitor tons of material for years without seeing a single interaction. Some experiments take the opposite approach, attempting to create dark matter particles in high-energy collisions at particle accelerators. If dark matter consists of particles that can be produced and detected in the laboratory, this could revolutionize our understanding of what fills the space around us. Direct detection of dark energy presents even greater challenges. Unlike dark matter, which clumps together and can potentially be caught through its interactions with normal matter, dark energy maintains a constant density throughout space and doesn't interact with anything except through its gravitational effects on cosmic expansion. Understanding dark energy may require entirely new theoretical frameworks that go beyond our current models of quantum field theory and general relativity. Some theories propose that dark energy arises from quantum fluctuations in extra dimensions that we can't directly observe. Others suggest that our understanding of gravity itself needs to be modified on cosmic scales. The cosmic microwave background radiation provides our most precise information about the early universe and the fundamental parameters that govern how space evolves. This ancient light, released when the universe first became transparent, carries the imprint of quantum fluctuations that existed when the cosmos was smaller than an atomic nucleus. These fluctuations, stretched to cosmic scales during the brief period of cosmic inflation, became the seeds for every structure we see today. The tiny temperature variations in the cosmic microwave background, measured to incredible precision by space-based telescopes, reveal the initial conditions that led to galaxies, stars, planets, and ultimately life itself. The pattern of these fluctuations tells us that space is geometrically flat on the largest scales, meaning that parallel lines will never meet, no matter how far they extend. This geometric flatness has profound implications for cosmic evolution and suggests that the total energy content of the universe might be exactly zero, with positive mass energy balanced by negative gravitational potential energy. Cosmic inflation itself represents one of the most dramatic examples of how space can behave under extreme conditions. During the first tiny fraction of a second after the Big Bang, space expanded exponentially, growing faster than the speed of light and stretching quantum fluctuations to macroscopic scales. This wasn't matter moving through space faster than light. This was space itself, expanding so rapidly that distant regions were carried apart faster than light could travel between them. The end of inflation triggered a phase transition that filled space with the hot plasma that would eventually cool to form the cosmic microwave background. But inflation might not have ended everywhere at the same time. Some theories propose that inflation continues eternally in other regions of space, creating an infinite multiverse where our observable universe is just one bubble among countless others. If eternal inflation is correct, then space extends far beyond our cosmic horizon and contains regions with different physical properties, different constants of nature, and perhaps entirely different forms of matter and energy. These other regions would be forever beyond our reach, separated from us by space expanding faster than light. The quantum vacuum continues to reveal new surprises as our experimental techniques become more sophisticated. Recent experiments have probed whether space has a preferred direction or handedness, testing fundamental assumptions about the symmetries of spacetime. Other experiments search for axions, hypothetical particles that could make up dark matter and might be detectable through their interaction with strong magnetic fields. The Casimir effect, which we discussed earlier, has been extended to more complex geometries that could potentially create repulsive forces or even exotic materials with negative energy density. While these possibilities remain highly speculative, they illustrate how the quantum properties of space might someday be harnessed for technological applications. Virtual particles in the quantum vacuum might also play a role in cosmic evolution that we're only beginning to understand. Some theories suggest that quantum fluctuations could influence the behavior of dark matter or even contribute to dark energy. The boundary between quantum mechanics and cosmology continues to blur as we discover connections between the smallest and largest scales in nature. Wormholes represent perhaps the most speculative but fascinating possibility for how space might be connected in ways we don't yet understand. These hypothetical tunnels through space-time could link distant regions of the universe or even connect to other universes entirely. While no wormholes have ever been detected, they're mathematically consistent with Einstein's equations under certain exotic conditions. If wormholes exist, they would require exotic matter with negative energy density to remain stable. This exotic matter would need properties unlike anything in the known universe, making wormholes seem more like science fiction than science fact. Yet the mathematical possibility remains, and some physicists continue to explore whether quantum effects could stabilize these cosmic shortcuts. The holographic principle adds another layer of mystery to space's true nature. This idea, originally developed to resolve paradoxes about information falling into black holes, suggests that all the information in a volume of space can be encoded on its boundary. In other words, our three-dimensional experience of space might be a projection of information stored on a two-dimensional surface. If the holographic principle is correct, then space as we experience it is fundamentally illusory. The real degrees of freedom would exist on distant boundaries, with our familiar three-dimensional world emerging as a kind of cosmic hologram. This radical idea is supported by mathematical discoveries, showing that gravity in higher dimensions can be exactly equivalent to quantum field theory in fewer dimensions. String theory pushes these concepts even further, suggesting that the fundamental building blocks of reality are tiny vibrating strings existing in 10 or 11 dimensions. Most of these extra dimensions would be compactified so small that we can't detect them directly, but they would still influence the properties of particles and forces in our three-dimensional space. In string theory, even the concept of space becomes emergent rather than fundamental. Space and time might arise from quantum entanglement between underlying string degrees of freedom, similar to how the smooth surface of a lake emerges from the complex interactions of countless water molecules underneath. Loop quantum gravity offers an alternative approach, proposing that space itself is quantized at the Planck scale into discrete units, about 10 to the negative 35th meters in size. At these unimaginably small scales, space would have a granular structure like a cosmic mesh, with the smooth geometry of Einstein's space-time emerging only as an approximation at larger scales. The implications of quantized space are profound. It could resolve the paradoxes that arise when quantum mechanics meets general relativity, providing a framework for understanding what happens at the center of black holes or during the first moments of cosmic inflation. It might also explain why space appears smooth on large scales, despite being fundamentally discrete at the smallest scales. Recent advances in quantum information theory have revealed deep connections between space, time, and information processing that are revolutionizing theoretical physics. The ADS-CFT correspondence shows that gravity in a higher dimensional space can be exactly equivalent to quantum field theory on its boundary, suggesting that space-time itself might be an emergent phenomenon arising from quantum entanglement. These discoveries are leading to a new understanding of space as an active information processing system, constantly computing the quantum correlations that give rise to our experience of reality. The geometry of space-time could emerge from the pattern of entanglement between different regions, with gravity itself being a manifestation of information geometry rather than a fundamental force. As our observational tools continue to improve, we're discovering that space operates according to principles that challenge our most basic assumptions about reality. The James Webb Space Telescope is revealing galaxies that formed when the universe was less than 5% of its current age, showing us how space looked when it was filled with the first generation of massive stars and supermassive black holes. These early galaxies appear larger and more massive than our models predicted, suggesting that star formation and galaxy assembly proceeded more rapidly in the early universe than we thought possible. The space between these ancient galaxies was filled with a different mix of elements, radiation, and physical conditions that created an environment unlike anything we see today. Gravitational wave astronomy continues to reveal new aspects of how space behaves during the most violent events in the universe. Each detected merger provides information about the masses, spins, and orbital dynamics of black holes and neutron stars, building a census of these extreme objects and revealing how they form and evolve over cosmic time. Future gravitational wave detectors will observe mergers of supermassive black holes, probe the structure of neutron star interiors, and potentially detect gravitational waves from cosmic phase transitions in the early universe. These observations will reveal how space itself responds to extreme conditions, and how gravitational wave propagation is affected by the cosmic expansion and the presence of dark matter and dark energy. The search for extraterrestrial life is also changing how we think about space as a potentially habitable environment. The discovery of thousands of exoplanets has revealed that planetary systems are common throughout the galaxy, with many worlds existing in the habitable zones around their stars, where liquid water could exist on their surfaces. But life might also exist in environments we previously considered sterile. The interstellar medium contains complex organic molecules, including amino acids and other building blocks of life. Rogue planets ejected from their parent systems might harbor subsurface oceans heated by radioactive decay. Even the space around brown dwarfs, failed stars too small to sustain fusion, might provide environments where life could emerge and evolve. The study of extremophile organisms on Earth has expanded our understanding of where life might exist in space. These hardy creatures survive in conditions that would kill most other life forms, from the intense radiation around nuclear reactors to the crushing pressures at the bottom of the ocean. If life can adapt to such extreme conditions on Earth, it might also survive in the harsh environment of interplanetary or interstellar space. As we continue pushing the boundaries of our understanding, space emerges not as a simple vacuum or empty container, but as a complex, dynamic, multi-layered environment that operates according to principles we're only beginning to grasp. Every region of space, from the quantum foam at the smallest scales to the cosmic web spanning billions of light years, reveals new physics and new mysteries that challenge our basic assumptions about reality. The space immediately around you contains quantum fields fluctuating at frequencies beyond imagination. Dark matter particles streaming through your body without interacting. Cosmic microwave background photons carrying information from the early universe. Neutrinos from stellar cores and the Big Bang itself. Gravitational waves from distant black hole mergers, and electromagnetic fields from sources throughout the galaxy and beyond. You're not sitting in empty space. You're immersed in a rich, invisible ocean of cosmic activity that connects you to every scale of reality, from the quantum vacuum to the cosmic horizon. The atoms in your body were forged in the cores of ancient stars. The water you drink contains hydrogen nuclei formed in the first few minutes after the Big Bang. And the space around you buzzes with virtual particles that pop in and out of existence faster than any measurement could detect. This realization fundamentally transforms our understanding of our place in the cosmos. We're not isolated beings on a small planet surrounded by empty void. We're integral components of a vast, interconnected system where quantum mechanics, relativity, thermodynamics, and information theory work together to create the rich tapestry of space that surrounds us. The story of space continues to unfold with each new discovery, revealing additional layers of complexity and beauty that stretch our imaginations and challenge our understanding of what it means to exist in this universe. From the quantum uncertainty that governs virtual particles to the dark energy that drives cosmic acceleration, space operates according to principles that are simultaneously elegant and mysterious, familiar and alien. And perhaps most remarkably, we're just at the beginning of this journey of discovery. Every answer we find leads to new questions. Every observation reveals phenomena we never expected. And every theoretical breakthrough opens new possibilities for understanding what space is actually made of. The universe continues to surprise us, and space itself remains the most fascinating, complex, and mysterious environment we've ever encountered. What's truly staggering is how space itself acts as both architect and construction material for everything we see in the universe. Think about it like this. When you look at a skyscraper, you see steel beams, concrete slabs, and glass windows. But the space between those components isn't just empty air. It's an active participant in holding the entire structure together, channeling forces, distributing weight, and allowing the building to flex without collapsing. Now imagine that same principle operating on cosmic scales, except the construction materials are dark matter, dark energy, quantum fields, and electromagnetic radiation. The space between galaxies isn't just a gap waiting to be filled. It's the medium through which gravitational waves propagate, the reservoir where dark energy resides, and the highway along which matter and energy travel from one cosmic structure to another. Recent discoveries have revealed that space operates like a vast information processing network. Every interaction between particles, every gravitational wave, every electromagnetic field carries data about the conditions where it originated. Space doesn't just store this information temporarily. It preserves patterns and correlations across billions of years, creating a cosmic memory bank that astronomers can read by observing distant objects. Consider what happens when we look at a galaxy 10 billion light years away. The light reaching our telescopes left that galaxy when the universe was less than a quarter of its current age. But that light didn't just travel through empty space for 10 billion years. It interacted with intervening matter, was deflected by gravitational fields, and was stretched by cosmic expansion. Each photon carries a record of every environment it encountered along its journey. This means that space functions as a cosmic archaeological site where evidence of past events remains embedded in the radiation fields, particle distributions, and geometric structure of space-time itself. We can literally read the history of the universe by studying how space has evolved and what traces different epochs have left behind. The temperature of space tells another fascinating story. In the emptiest regions between galaxy clusters, space maintains a temperature of about 2.7 degrees above absolute zero, set by the cosmic microwave background radiation. But this isn't a uniform temperature. Tiny variations, measured at the level of millionths of a degree, reveal the quantum fluctuations that existed when the universe was smaller than a golf ball. These temperature patterns aren't random. They follow specific mathematical relationships that encode information about the fundamental constants of physics, the composition of the universe, and the processes that operated during cosmic inflation. By mapping these temperature variations with incredible precision, cosmologists can determine how much dark matter exists, how fast space is expanding, and what conditions were like in the first fraction of a second after the Big Bang. But space's temperature isn't just a passive record of cosmic history. It actively influences how matter behaves throughout the universe. Gas clouds falling into galaxy clusters get heated to millions of degrees as they crash into the hot intracluster medium. This heating prevents them from cooling and forming new stars, effectively shutting down star formation across vast regions of space. Meanwhile, in the densest regions where galaxies are actively forming stars, space becomes filled with stellar winds, supernova shock waves, and radiation pressure that can either trigger new star formation or blow gas completely out of the galaxy. The feedback between stars and the surrounding space creates complex cycles of heating and cooling that regulate how efficiently galaxies convert their gas into stars. Magnetic fields threading through space add another layer of complexity to these processes. Unlike gravity, which only attracts, magnetic fields can both attract and repel charged particles, creating channels and barriers that guide the flow of cosmic rays and plasma throughout the universe. These fields are generated by rotating stars, accretion disks around black holes, and the motion of conducting fluids in planetary cores. The magnetic field of our own galaxy, the Milky Way, forms a complex spiral structure that follows the galaxy's rotation pattern. This field influences how cosmic rays propagate through interstellar space, affects the formation of molecular clouds where stars are born, and helps channel material toward the supermassive black hole at our galaxy's center. On larger scales, magnetic fields connect entire galaxy clusters through filaments that span tens of millions of light years. These intergalactic magnetic highways can transport energy and particles across enormous distances, linking the evolution of galaxies that would otherwise seem completely independent. Radio telescopes reveal vast structures in space that are invisible to optical observations. Lobes of radio emission from active galactic nuclei extend far beyond their host galaxies, creating bubbles in the intergalactic medium that can influence star formation in neighboring galaxies. These radio sources show us that space is crisscrossed with jets, bubbles, and shock fronts created by some of the most powerful engines in the universe. Pulsars, rapidly spinning neutron stars, act like cosmic lighthouses whose precisely timed radio pulses sweep across space. By monitoring these pulses with incredible accuracy, astronomers can detect gravitational waves passing through our local region of space. The entire galaxy becomes a gravitational wave detector, with pulsars serving as the measurement devices and space itself as the medium being monitored. The precision required for these measurements is almost incomprehensible. We're talking about detecting changes in the arrival time of pulsar signals at the level of nanoseconds, caused by gravitational waves that stretch and compress space by amounts smaller than the size of atomic nuclei. The fact that we can make such measurements demonstrates both the exquisite regularity of pulsar timing and the incredible sensitivity that modern technology can achieve. Neutrinos add yet another invisible component to space's composition. These ghostly particles are produced in such enormous quantities by stars, supernovas, and cosmic ray interactions that space is absolutely flooded with them. Trillions pass through every square centimetre of space every second, carrying information about nuclear processes operating in stellar cores and other extreme environments. What makes neutrinos particularly fascinating is their ability to escape from regions where photons cannot. When a massive star's core collapses to form a neutron star, the core becomes so dense that photons can't escape for hours or even days. But neutrinos stream out immediately, carrying the first news of the collapse to the rest of the universe. Space becomes a communication network where neutrinos serve as messengers from the most inaccessible regions of cosmic catastrophes. The IceCube Neutrino Observatory, buried deep in Antarctic ice, has detected neutrinos from distant galaxies and gamma-ray bursts, opening an entirely new window into high-energy processes operating throughout the universe. These observations show that space is filled with neutrinos carrying energies millions of times higher than anything produced in terrestrial particle accelerators. Some of these ultra-high energy neutrinos might come from interactions between cosmic rays and the cosmic microwave background radiation, revealing processes that occur when the highest energy particles in the universe collide with the most ancient photons. Others might be produced near supermassive black holes, where matter is accelerated to incredible energies before disappearing beyond the event horizon. The cosmic ray spectrum itself tells a remarkable story about conditions throughout our galaxy and beyond. These high-energy particles, mostly protons and heavier nuclei, are accelerated by supernova remnants, pulsar wind nebulae, and other violent events. They stream through space in all directions, creating a background of high-energy radiation that affects everything from satellite electronics to the evolution of planetary atmospheres. The highest energy cosmic rays carry so much energy that their origin remains mysterious. These particles have energies comparable to a tennis ball traveling at highway speeds, concentrated in a single atomic nucleus. The fact that such particles exist tells us that space contains acceleration mechanisms far more powerful than anything we can create artificially. When these ultra-high energy cosmic rays interact with the cosmic microwave background, they should lose energy through a process called the GZK cutoff. This creates a horizon beyond which the highest energy cosmic rays cannot reach us, similar to how cosmic expansion creates a horizon beyond which we cannot see distant galaxies. The study of this cosmic ray horizon provides another probe of space's large-scale structure and composition. Gamma-ray astronomy reveals even more extreme processes operating in space. Gamma-ray bursts, the most powerful explosions since the Big Bang, release more energy in a few seconds than our Sun will produce in its entire lifetime. These events occur when massive stars collapse into black holes or when neutron stars merge, creating conditions so extreme that they challenge our understanding of fundamental physics. The space around gamma-ray bursts becomes a laboratory for studying matter and energy under conditions that cannot be replicated anywhere else. The intense radiation field creates electron-positron pairs from the quantum vacuum, while powerful magnetic fields accelerate particles to energies approaching the theoretical maximum allowed by interactions with cosmic microwave background photons. Some gamma-ray bursts are so distant that their light has traveled for most of the age of the universe to reach us. These ancient explosions occurred when space was much denser and hotter than it is today, filled with the first generation of massive stars that contained almost no heavy elements. By studying these distant bursts, astronomers can probe conditions in the early universe when space was undergoing rapid chemical evolution, as the first stars began producing carbon, oxygen, and other elements necessary for planet formation. The afterglows of gamma-ray bursts reveal how the explosion energy propagates through the surrounding medium, creating shockwaves that sweep up interstellar material and accelerate it to incredible velocities. These observations show that space near massive stars is often filled with material ejected by stellar winds, creating complex environments where gas densities, magnetic field strengths, and radiation levels vary dramatically over relatively small distances. Blazars, active galactic nuclei whose jets point directly toward Earth, show us how space can be transformed by the most powerful engines in the universe. These objects accelerate particles to energies where they emit gamma rays through interactions with starlight and cosmic microwave background photons. The jets from blazars can extend for millions of light years, creating channels through space where relativistic particles stream at speeds approaching that of light. The fact that we can observe these jets across such enormous distances tells us something profound about the nature of space itself. The material in these jets maintains its collimation and energy over scales comparable to the distance between galaxy clusters, suggesting that space provides remarkably little resistance to the propagation of organized high-energy flows. Variable sources like blazars also demonstrate that space can change dramatically on timescales ranging from minutes to years. Flares from these objects can increase their brightness by factors of thousands, indicating that the space immediately around supermassive black holes is a dynamic, turbulent environment where accretion rates, magnetic field configurations, and jet properties can change rapidly. The polarization of light from these sources reveals that space around active galactic nuclei is threaded with highly organized magnetic fields that can maintain their structure even in the presence of turbulent gas flows and relativistic particle beams. These observations provide crucial tests of our understanding of how magnetic fields behave in the most extreme environments the universe has to offer. Quasars, the most luminous objects in the universe, show us how space looked when cosmic structure was first emerging from the primordial density fluctuations. These objects are powered by supermassive black holes that somehow grew to billions of solar masses when the universe was less than 1 billion years old. Understanding how such massive black holes formed so early requires detailed knowledge of how gas flowed through space and accumulated in the first galactic halos. The space between Earth and distant quasars acts like a cosmic laboratory for studying how matter is distributed throughout the universe. As quasar light travels toward us, it passes through gas clouds, galaxy halos, and the intergalactic medium. Each of these environments leaves its signature in the quasar spectrum, allowing astronomers to map the distribution of matter along the entire line of sight. This technique, called the Lyman alpha forest, reveals that space is filled with a complex web of gas filaments connecting galaxies across vast distances. The properties of this gas, its temperature, density, and chemical composition provide crucial information about how cosmic structure evolved and how galaxies acquired the material they needed to form stars. Gravitational lensing provides another powerful tool for mapping the distribution of matter in space including the dark matter that doesn't emit light. When light from a distant galaxy passes near a massive foreground object, the gravity of that object bends the light rays, creating distorted or multiple images of the background galaxy. By studying these lensing effects, astronomers can map the distribution of dark matter with incredible precision. The results reveal that space is filled with dark matter structures on all scales, from the halos surrounding individual galaxies to the vast filaments connecting galaxy clusters across hundreds of millions of light years. Strong lensing events, where the foreground mass creates multiple images, or Einstein rings, show that space near massive galaxies and galaxy clusters is so severely curved that light rays can follow multiple paths between source and observer. These observations provide direct visual evidence for Einstein's prediction that massive objects warp the geometry of space-time. Weak lensing, where the distortions are too small to see in individual galaxies, but can be detected statistically across large surveys, reveals the cosmic web structure on the largest scales. By measuring tiny shape distortions in millions of distant galaxies, astronomers can map how dark matter is distributed throughout space and how cosmic structure has evolved over billions of years. The cosmic web itself represents the largest scale organization of matter and energy in space. Computer simulations show that this structure emerged naturally from tiny quantum fluctuations in the early universe, amplified by gravity over billions of years of evolution. Dark matter collapsed first into filaments and nodes, creating the scaffolding along which normal matter could flow and accumulate. Galaxy formation occurs preferentially at the intersections of dark matter filaments, where the gravitational potential wells are deepest and gas can most easily cool and condense into stars. The space between these filaments, the cosmic voids, contains very little matter and represents some of the most empty regions in the observable universe. But even cosmic voids aren't completely empty. They contain sparse populations of galaxies, dark matter substructure, and the warm, hot intergalactic medium that may hold up to half of all normal matter in the universe. The properties of void galaxies provide unique insights into how galaxy formation proceeds in the lowest density environment space has to offer. The expansion of space affects different regions differently depending on their local matter density. In high-density regions like galaxy clusters, gravity overcomes cosmic expansion and structures remain gravitationally bound. But in low-density regions like cosmic voids, expansion dominates and galaxies are carried away from each other at ever-increasing speeds. This differential expansion creates a hierarchy of cosmic structures that reflects the interplay between gravity and dark energy across different scales. Understanding this hierarchy requires detailed knowledge of how space expands, how matter moves through this expanding space, and how the two processes influence each other over cosmic time. Dark energy surveys are mapping the expansion history of space by observing distant supernovas, galaxy clusters, and other standard candles across a range of cosmic epochs. These observations reveal that cosmic expansion has not been constant, but has gone through periods of deceleration and acceleration as the relative influence of matter and dark energy has changed. The transition from matter-dominated to dark energy. Dominated expansion occurred about 5 billion years ago, roughly when our solar system was forming. Before this transition, space was expanding at a decreasing rate as gravity fought against the expansion. After the transition, dark energy began to dominate and cosmic expansion started accelerating. This acceleration has profound implications for the future evolution of space and the ultimate fate of cosmic structure. If dark energy continues to drive accelerating expansion, Eventually, galaxies beyond our local group will be carried so far away that they disappear beyond the cosmic event horizon. Future civilizations will see a much emptier universe than we observe today. The local group itself, bound together by gravity, will eventually merge into a single large galaxy surrounded by empty space. Stars will continue forming for trillions of years, but eventually the supply of gas will be exhausted and star formation will cease. The space around the remaining stars will grow ever colder and emptier as cosmic expansion carries away the cosmic microwave background radiation. But that's looking far into the future. For now, space continues to surprise us with new discoveries that challenge our understanding and reveal additional layers of complexity. Each new telescope, each new detector, each new theoretical framework opens windows into aspects of space that we never knew existed. The James Webb Space Telescope is revealing galaxies that formed when the universe was less than 5% of its current age, showing us how space looked when it was filled with the first generation of stars and black holes. These early galaxies appear to have formed more quickly and grown more massive than our models predicted, suggesting that the processes operating in early cosmic space were more efficient than we thought possible. Future gravitational wave observatories will detect mergers involving supermassive black holes, revealing how these monsters grew and merged as cosmic structure evolved. These observations will show us how space itself responded to the most violent events in cosmic history, and how gravitational wave propagation was affected by the changing composition and geometry of the universe. Next-generation particle detectors will push the search for dark matter to new levels of sensitivity, potentially revealing whether this mysterious component of space consists of familiar particles or something entirely new to physics. The discovery of dark matter particles would revolutionize our understanding of what space contains and how it has evolved since the Big Bang. Since quantum experiments continue probing the vacuum itself with unprecedented precision, testing whether space has preferred directions, whether virtual particles behave exactly as theory predicts, and whether new physics emerges at the highest energy scales. These investigations might reveal that space has structure and properties we haven't yet imagined. The search for extraterrestrial life is expanding our understanding of space as a potentially life-bearing environment. The discovery of thousands of exoplanets has shown that planetary systems are common throughout the galaxy, with many worlds existing in conditions where liquid water could exist and life might emerge. But life might also exist in environments we previously considered impossible. The interstellar medium contains complex organic molecules that could serve as building blocks for biological processes. Rogue planets ejected from their parent systems might harbor subsurface oceans heated by radioactive decay. Even the space around brown dwarfs might provide niches where life could survive and evolve. As our understanding of space continues to evolve, we're discovering that it operates according to principles that span the entire range, from quantum mechanics to cosmic evolution. Every cubic centimeter contains quantum fields, virtual particles, electromagnetic radiation, and gravitational effects that connect local processes to the largest scales of cosmic structure. The realization that space is not empty, but filled with invisible activity, fundamentally changes our perspective on our place in the universe. We're not isolated beings on a small planet surrounded by void. We're embedded in a rich, dynamic environment that connects us to every scale of reality. From the quantum fluctuations in the vacuum around us to the cosmic web spanning billions of light years. This cosmic perspective reveals that space is simultaneously the most familiar and most mysterious aspect of our existence. We move through it every day, yet it contains components and operates according to principles that challenge our most basic assumptions about reality. The story of space is still being written, and every new discovery adds another chapter to this cosmic epic that connects the smallest and largest scales of nature in ways we're only beginning to understand. The study of space reveals patterns that operate across scales so vast they challenge our ability to comprehend them. Consider how information travels through this cosmic medium. When we observe a distant galaxy, we're not just seeing light that happened to wander in our direction. We're receiving a carefully encoded message that carries data about temperature, chemical composition, velocity, magnetic field strength, and dozens of other properties from its point of origin. But here's where it gets absolutely mind-bending. That information doesn't just travel passively through space. The medium itself modifies, filters, and sometimes amplifies the signal along its journey. Gravitational fields bend light rays, changing the apparent position and brightness of distant objects. Magnetic fields rotate the polarization of electromagnetic waves. Dust grains absorb certain wavelengths while scattering others. Gas clouds imprint their own spectroscopic signatures onto the passing radiation. By the time that ancient photon reaches your eye or telescope, it carries not just information about its source, but a complete record of every environment it encountered during its billion-year journey. Space functions as both communication channel and data processor, encoding the history of cosmic evolution into every beam of light that crosses the universe. This information processing capability extends far beyond electromagnetic radiation. Gravitational waves carry different types of data about their sources, revealing the masses, spins, and orbital dynamics of merging black holes in ways that no other messenger could provide. Cosmic rays transport information about acceleration mechanisms operating in the most extreme environments. Neutrinos bring news from the cores of stars and the hearts of supernovas where no other particle could escape. Even the quantum vacuum participates in this cosmic information network. Virtual particles that pop in and out of existence aren't random events, but carefully orchestrated quantum fluctuations that preserve information about the local energy density, temperature, and field configuration. The Heisenberg uncertainty principle ensures that this quantum information processing never stops, creating a background of constant computational activity that permeates every corner of space. Recent discoveries in quantum information theory suggest that space itself might be the universe's ultimate computer, processing quantum correlations and entanglement patterns that give rise to the familiar properties of matter, energy, and space-time geometry. This isn't science fiction speculation. It's a serious theoretical framework supported by mathematical discoveries showing deep connections between information theory, quantum mechanics, and gravity. The implications are staggering. Every interaction between particles, every measurement, every observation might be part of a vast computational process where space calculates the quantum correlations that determine what happens next. The future state of the universe emerges from quantum calculations performed by the structure of space-time itself. But let's bring this down to more tangible scales and consider how space behaves in environments we can actually study. The region around our own planet reveals incredible complexity that most people never think about. Earth's magnetosphere isn't just a protective bubble. It's a dynamic plasma environment where charged particles from the solar wind interact with our planet's magnetic field in ways that create some of the most beautiful and violent phenomena in our local cosmic neighborhood. Auroras represent just the visible tip of this cosmic iceberg. The same processes that create those dancing curtains of light in polar skies also accelerate particles to dangerous energies, disrupt satellite communications, and can even affect power grids on the ground. The space around Earth buzzes with electrical currents, magnetic field fluctuations, and plasma waves that would be completely alien to anyone who thinks of space as empty and quiet. Van Allen radiation belts trap charged particles in complex orbital patterns around our planet, creating regions where spacecraft must be carefully shielded to avoid electronic damage. These belts expand and contract with solar activity, sometimes growing so large they extend beyond the orbit of geosynchronous satellites. During major solar storms, the radiation environment in near-Earth space can become temporarily more dangerous than the surface of Mars. The solar wind itself reveals how space can be simultaneously uniform and wildly variable. This stream of charged particles flows outward from the Sun at speeds exceeding 1,000,000 miles per hour, carrying the solar magnetic field throughout the entire solar system. But it's not a smooth, steady flow. It's filled with turbulence, shock waves, magnetic field reversals, and high-speed streams that create constantly changing conditions throughout interplanetary space. When high-speed solar wind streams overtake slower-moving material, they create compression regions that can accelerate particles and generate powerful magnetic disturbances. These events propagate through space like cosmic weather fronts, affecting planets, comets, and spacecraft across the entire solar system. The space between worlds isn't static. It's a dynamic fluid environment with its own meteorology and climate patterns. Comets provide spectacular demonstrations of how space interacts with small bodies in our solar system. As these dirty snowballs approach the Sun, solar radiation and particle bombardment sublimate material from their surfaces, creating the iconic tails that can stretch for millions of miles. But there are actually two types of comet tails, revealing different aspects of how space affects these visitors from the outer solar system. The dust tail, pushed away from the Sun by radiation pressure, shows how electromagnetic energy can transfer momentum to matter across vast distances. The ion tail, shaped by magnetic fields in the solar wind, reveals how charged particles interact with the complex electromagnetic environment of interplanetary space. Watching a comet develop and lose its tails is like seeing space itself sculpt these ancient objects in real time. Interplanetary dust adds another layer of complexity to space within our solar system. This material, mostly debris from comets and asteroids, creates a diffuse cloud that extends from the inner solar system out beyond the orbit of Jupiter. Spacecraft traveling through this environment encounter constant bombardment by particles ranging from microscopic grains to pebble-sized chunks. The Pioneer and Voyager spacecraft, now in interstellar space, experienced measurable drag from this interplanetary medium during their journeys through the outer solar system. This resistance, though incredibly small, was enough to slightly alter their trajectories and provide information about the density and distribution of material in regions far from the Sun. The heliopause, where our solar system meets interstellar space, represents one of the most dramatic boundaries in our cosmic neighborhood. Voyager 1 and 2 have now crossed this boundary and are sending back data about conditions in the local interstellar medium. The results are surprising. Interstellar space is denser, more turbulent, and more magnetically active than scientists expected. The local bubble, a cavity in the interstellar medium created by ancient supernova explosions, extends for hundreds of light years around our solar system. This region has lower density than typical interstellar space, but it's still filled with hot gas at temperatures of about 1,000,000 degrees. The X-ray glow from this hot gas is detectable by space-based telescopes, revealing the three-dimensional structure of our local cosmic environment. Moving beyond our immediate neighborhood, the Orion arm of our galaxy provides an excellent laboratory for studying how space behaves in a typical spiral galaxy environment. This region contains a mix of young, hot stars that heat and ionize the surrounding gas, older stars that contribute steady stellar winds, and the remnants of ancient supernovas that have carved bubbles and cavities in the interstellar medium. Stellar nurseries like the Orion Nebula show how space can transform from a relatively quiet environment into a cauldron of star formation activity. The gravitational collapse of giant molecular clouds creates protostars that heat their surroundings to thousands of degrees. Stellar winds and radiation pressure from newly formed massive stars can blow away the remaining gas, terminating star formation and dispersing heavy elements throughout the surrounding region. These feedback processes operate on timescales ranging from thousands to millions of years, creating a complex ecosystem where star formation, stellar evolution, and the properties of interstellar space are intimately connected. The space between stars isn't just a passive reservoir of material waiting to form new stars. It's an active participant in regulating how efficiently gas can cool, collapse, and ignite nuclear fusion. Superbubbles created by multiple supernova explosions can grow to enormous sizes, sometimes breaking out of the galactic disk entirely and venting hot gas into the galactic halo. These structures show that space in spiral galaxies is highly interconnected, with events in one region affecting conditions hundreds or thousands of light years away. The center of our galaxy reveals even more extreme conditions. Sagittarius. A star, our central supermassive black hole, creates an environment where space is warped by intense gravity, heated by powerful radiation, and stirred by relativistic jets and winds. Stars orbit this black hole at speeds exceeding 5,000 miles per second, providing direct tests of Einstein's general relativity in the strong field regime. The space immediately around Sagittarius, a star, is filled with hot plasma, magnetic fields, and high-energy particles that create a complex, time-variable environment. Radio telescopes reveal filamentary structures extending for hundreds of light years from the galactic center, suggesting that the central black hole influences conditions throughout a significant portion of our galaxy's inner regions. Other galaxies provide natural laboratories for studying how space behaves under different conditions. Elliptical galaxies, with their older stellar populations and hot gas atmospheres, show us environments where star formation has largely ceased, and space is dominated by stellar winds from evolved stars and energy input from central black holes. Starburst galaxies, where star formation proceeds at rates hundreds of times higher than in the Milky Way, reveal how space responds to extreme levels of energy input. These galaxies often drive powerful galactic winds that can expel gas at speeds of thousands of kilometers per second, showing that intense star formation can fundamentally alter the properties of space throughout an entire galaxy. Galaxy interactions and mergers create some of the most dynamic environments in the universe. When two galaxies collide, their gravitational fields distort each other's structure, triggering bursts of star formation and feeding material onto their central black holes. The space between the galaxies becomes a battlefield where tidal forces, shock waves, and gravitational torques reshape both stellar and gas distributions. The antennae galaxies, currently in the midst of a major merger, show how these interactions can transform space on galactic scales. Star formation rates increase dramatically in the collision zone, while tidal tails of stars and gas extend for hundreds of thousands of light years. The space throughout this system is filled with shock fronts, turbulent gas flows, and newly formed star clusters that will eventually disperse throughout the merged galaxy. Galaxy clusters reveal how space behaves in the highest density environments the universe has to offer. The intracluster medium, hot plasma at temperatures of tens of millions of degrees, fills the space between galaxies and outweighs all the stars in all the cluster galaxies combined. This plasma is so hot, it glows brightly in X-rays, revealing complex structures shaped by galaxy motions, magnetic fields, and the underlying dark matter distribution. When galaxy clusters merge, they create some of the most energetic events since the Big Bang. These cosmic collisions generate shock waves that span millions of light years and accelerate particles to incredible energies. Radio telescopes reveal vast regions of synchrotron emission, where relativistic electrons spiral around magnetic field lines, creating diffuse halos and relics that trace the history of cluster formation. The Coma cluster, one of the nearest large galaxy clusters, contains thousands of galaxies embedded in a hot plasma atmosphere that extends far beyond the visible galaxy distribution. This cluster has been extensively studied across the electromagnetic spectrum, revealing how space in these extreme environments supports phenomena that have no analogue in our local cosmic neighborhood. Active galactic nuclei add another dimension to our understanding of space in cluster environments. These powerful sources can inflate radio lobes that extend far beyond their host galaxies, creating cavities in the hot intracluster medium and affecting star formation throughout the cluster. The energy released by these sources is sufficient to balance radiative cooling of the cluster gas, preventing runaway cooling flows that would otherwise consume the entire gas supply. Moving to the largest scales, the cosmic web structure reveals how space organizes matter and energy across billions of light years. This vast network of dark matter filaments and nodes represents the fundamental architecture of the universe, shaped by gravity acting on primordial quantum fluctuations over cosmic time. Computer simulations show that this structure is hierarchical, with smaller structures merging to form larger ones in a process that continues today. Galaxy formation occurs preferentially at the intersections of dark matter filaments, where deep potential wells can trap gas and trigger star formation. The properties of these cosmic environments, from their dark matter content to their gas temperature and magnetic field strength, determine how efficiently galaxies can form and evolve. Cosmic voids, the largest empty regions in the universe, provide unique insights into how space behaves in the lowest density environments. These regions, spanning hundreds of millions of light years, contain very few galaxies and represent natural laboratories for studying galaxy formation under conditions of minimal environmental influence. Void galaxies tend to be smaller, bluer, and more actively star-forming than galaxies in dense environments, suggesting that the properties of space itself influence how galaxies acquire gas, form stars, and evolve over time. The expansion of space proceeds differently in void regions, where dark energy dominates over matter density, compared to dense regions where gravity can overcome cosmic expansion. The warm, hot intergalactic medium, a diffuse plasma that may contain up to half of all normal matter in the universe, fills the space between galaxies and provides a reservoir of baryons that could fuel future star formation. This medium is so tenuous and at such specific temperatures that it's nearly invisible to most observational techniques, yet it represents a major component of cosmic matter that we're only beginning to understand. Recent observations using the technique of kinematic Sunyaev-Zeldovich effect have begun to map the distribution of this missing baryonic matter, revealing how it traces the cosmic web structure and connects the evolution of galaxies to the large-scale environment. Understanding this component is crucial for completing our inventory of what space actually contains and how matter flows between different cosmic reservoirs. Primordial gravitational waves, if they exist, would provide the ultimate probe of space's earliest conditions. These ripples in space-time, generated during cosmic inflation, would carry information about quantum processes operating when the universe was smaller than an atomic nucleus. Detecting these primordial waves would require space-based gravitational wave observatories with laser arms millions of miles long, turning the solar system itself into a detector for these ancient echoes. The cosmic neutrino background represents another component of space that remains largely undetected despite its ubiquity. These relic neutrinos, produced in the first few seconds after the Big Bang, should fill space with a density of about 300 particles per cubic centimeter. Unlike the cosmic microwave background, which we can observe directly, the cosmic neutrino background interacts so weakly with matter that detecting it requires experimental techniques at the very edge of current technology. Future experiments like Ptolemy aim to detect these relic neutrinos by observing their effect on tritium decay, potentially opening a new window into the universe's first seconds. Such observations would provide unprecedented information about conditions when space was filled with exotic particles and energy densities that can never be recreated in terrestrial laboratories. The ongoing expansion of space continues to be one of the most active areas of research in cosmology. Dark energy surveys are mapping how this expansion has changed over cosmic time, revealing that the acceleration began relatively recently in cosmic history. Understanding why this transition occurred and whether dark energy is truly constant or evolving with time remains one of the greatest challenges in modern physics. Type Ia supernovas, used as standard candles for measuring cosmic distances, have revealed that space expanded more slowly in the past when matter density was higher. The transition to accelerated expansion occurred about 5 billion years ago, roughly when our solar system was forming. This timing may be coincidental, or it might reflect deeper connections between local and cosmic evolution that we don't yet understand. Future space missions will push these measurements to higher precision and greater distances, potentially revealing whether dark energy has changed over cosmic time or remains truly constant. The answers to these questions will determine the ultimate fate of space itself and everything it contains. If dark energy continues to drive accelerating expansion at its current rate, the universe will eventually enter a phase where expansion becomes so rapid that it overcomes all other forces. This scenario, called the Big Rip, would see space expand so violently that it tears apart galaxy clusters, individual galaxies, stellar systems, and ultimately even atoms themselves. Alternatively, dark energy might weaken over time, allowing gravity to eventually halt and reverse cosmic expansion in a Big Crunch scenario. Or the expansion might continue but at a decreasing rate, leading to a cold, empty universe where space grows ever larger and more dilute until it reaches maximum entropy. Each of these possibilities represents a fundamentally different future for space and everything it contains. The fact that we can seriously contemplate such cosmic scenarios demonstrates how far our understanding has evolved from the simple notion of space as empty void. We now recognize space as a dynamic, evolving, information-rich environment that operates according to principles spanning quantum mechanics, relativity, thermodynamics, and information theory. As our observational capabilities continue to advance, we're discovering that space operates on principles that challenge our most basic intuitions about reality. Every new telescope, every new detector, every new theoretical framework reveals additional layers of complexity that connect the quantum and cosmic scales in unexpected ways. The realization that space is not empty but filled with fields, particles, and forces that influence every aspect of cosmic evolution fundamentally changes our understanding of existence itself. We're not observers standing outside the universe looking in. We're participants embedded in a vast, interconnected system where the quantum vacuum around us connects to the cosmic web spanning billions of light years. This cosmic perspective reveals space as simultaneously the most familiar and most mysterious aspect of our reality. We move through it constantly, yet it contains components and operates according to principles that push the boundaries of human understanding. The story of space continues to unfold with each new discovery, revealing a universe far stranger, more beautiful and more complex than our ancestors could have imagined. could have imagined. What makes this cosmic revelation even more profound is how space itself becomes the ultimate detective story, where evidence from billions of years ago remains embedded in the very fabric of reality around us. Every region tells a different chapter of this cosmic narrative, from the quantum fluctuations that ripple through your coffee cup to the dark matter streams flowing invisibly through your bedroom as you sleep. Consider the extraordinary fact that space preserves memory across unimaginable timescales. The photons hitting your retina right now from distant stars began their journey before human civilization existed. They've traveled through expanding space for millions or billions of years, carrying encrypted information about stellar temperatures, chemical compositions, and magnetic field strengths from cosmic neighborhoods we'll never visit. But here's what's absolutely staggering. Space doesn't just passively transmit this information. It actively processes and modifies every signal along the way. Gravitational fields act like cosmic lenses, bending light rays and sometimes creating multiple images of the same distant object. Magnetic fields twist the polarization of radio waves. Dust clouds filter certain colors while scattering others. By the time any photon reaches us, it carries not just data about its source, but a complete record of every environment it encountered during its epic journey. This makes space the universe's ultimate archaeological site. We can read the history of cosmic evolution by studying how different regions have processed and preserved information over billions of years. Galaxy collisions that happened before our solar system formed have left gravitational signatures we can still detect today. Supernova explosions from the dawn of star formation continue to influence the chemistry of gas clouds where new planets are being born right now. The precision of this cosmic record-keeping defies comprehension. Astronomers can measure the temperature of the early universe to within a few thousandths of a degree by studying tiny variations in the cosmic microwave background. They can determine how much dark matter exists by observing how it bends light from galaxies billions of light years away. They can even probe the first fraction of a second after the Big Bang by analyzing the abundance of different atomic nuclei throughout space. What emerges from these investigations is a picture of space as an active participant in cosmic evolution, rather than a passive stage where events unfold. The quantum vacuum doesn't just sit there bubbling with virtual particles. Those fluctuations influence the behavior of real particles, affect the stability of atoms, and may even play a role in determining the fundamental constants of physics. Dark matter doesn't just provide gravitational scaffolding for cosmic structure. It participates in complex feedback loops with normal matter, influencing where stars form, how galaxies evolve, and ultimately, where conditions become suitable for planets and life. The invisible architecture of reality shapes everything we can observe in ways we're only beginning to appreciate. Dark energy represents perhaps the most dramatic example of space's active role in cosmic evolution. This mysterious force doesn't just make the universe expand. It continuously creates new space between distant galaxies while maintaining its own constant density. This means the total amount of dark energy in the universe increases over time as expansion creates more volume for it to fill. Think about the implications of this process. Every second, cosmic expansion creates billions of cubic light years of new space, each containing its quota of dark energy. Where does this energy come from? How can the universe create something from nothing without violating conservation laws? These questions push the boundaries of our understanding and suggest that space itself might operate according to principles we haven't discovered yet. Recent theoretical advances propose that space and time might be emergent properties arising from more fundamental quantum information processing. In this view, the familiar three dimensions of space could be projections of data stored and processed in higher dimensional systems we can't directly observe. Your experience of moving through space might actually be the result of quantum correlations being computed by the universe's underlying information architecture. This isn't science fiction speculation. It's supported by mathematical discoveries showing deep connections between quantum entanglement, information theory, and the geometry of space-time. Some of the most successful theories in modern physics suggest that reality emerges from quantum calculations performed by the structure of space itself. But let's ground this cosmic perspective in phenomena we can actually observe and study. The space immediately around Earth reveals incredible complexity that most people never consider. Our planet's magnetosphere creates a dynamic boundary where solar wind particles interact with terrestrial magnetic fields in ways that generate some of the most spectacular and violent phenomena in our cosmic neighborhood. Aurora displays represent just the visible manifestation of these invisible cosmic processes. The same particle interactions that create dancing curtains of green and red light also accelerate charged particles to dangerous energies, disrupt satellite communications, and can even induce electrical currents in power grids thousands of miles away. The space around our planet buzzes with electromagnetic activity that would be completely alien to anyone expecting emptiness and silence. Solar storms demonstrate how quickly conditions in space can change. During major coronal mass ejections, the Sun hurls billions of tons of charged particles into interplanetary space at speeds exceeding 2 million miles per hour. When these plasma clouds reach Earth, they can compress our magnetosphere so violently that the protective boundary shrinks to half its normal size. Astronauts aboard the International Space Station must sometimes take shelter in the most heavily shielded sections of the spacecraft during these events. The radiation environment in low Earth orbit can become more dangerous than the surface of Mars within hours, as high-energy particles penetrate normally safe regions of space around our planet. These space weather events reveal how interconnected different regions of the solar system really are. Disturbances near the Sun's surface propagate through interplanetary space as shockwaves and magnetic field distortions that affect every planet, moon, and spacecraft in the solar system. Jupiter's powerful magnetosphere can generate radio bursts detectable on Earth. Saturn's rings create complex interactions with charged particles that produce spectacular displays invisible to optical telescopes, but readily observable at radio wavelengths. The Voyager spacecraft, now exploring interstellar space beyond the influence of our Sun, have discovered that even the boundary between solar and interstellar environments is far more complex than anyone expected. The heliopause isn't a simple barrier, but a dynamic region where two very different plasma environments interact through processes that generate turbulence, magnetic field fluctuations, and particle acceleration. Data from these intrepid explorers reveals that interstellar space itself is more active and structured than predicted. The local interstellar medium contains magnetic fields, cosmic rays, and complex chemical processes that create an environment unlike anything found within our solar system. We're not just sending spacecraft into empty void, we're exploring alien territories with their own physics and phenomena. The local bubble, a cavity in interstellar space carved by ancient supernova explosions, extends for hundreds of light years around our solar system. This region contains hot plasma at temperatures exceeding 1 million degrees, yet it's so diffuse that a spacecraft could travel through it without detecting anything unusual. The X-ray glow from this hot gas is visible to space-based telescopes, revealing the three-dimensional structure of our cosmic neighborhood. So, there you have it. Space isn't empty. It never was. From the quantum foam buzzing with virtual particles beneath your feet to the dark energy stretching the cosmic web across billions of light years, every cubic centimeter of reality pulses with invisible activity that connects you to the deepest mysteries of existence. You're not just sitting in a room reading this. You're immersed in the most complex, dynamic, an interconnected environment the universe has ever created. And we've barely scratched the surface of understanding what space is actually made of.